Alright, now let's get on to optimization. So, what is optimization? Optimization is the mathematics of finding the best possible way to achieve a certain goal. Alright, so what you'll typically see is how can we maximize area? How can we maximize profit? How can we minimize cost? Or anything like that. So, how do we solve these types of problems? We specify a function that we need to optimize, then use the same concepts in curve sketching, just with the function instead. So, a few examples of what you might see are written here. Maximizing profit, maximizing volume, and then a pretty common example is maximizing volume of a box built from a sheet of cardboard. That's a very common one. Many optimization questions will ask you to rearrange an equation, or they won't even give you an equation at all. They'll just tell you a little bit of information about the scenario. And then from there, you will need to create an equation yourself. So drawing a diagram usually is very, very useful for these types of questions. All right. So let's go through our example here. If x plus y equals 8, express p equals x squared plus y squared in terms of x only. Alright, so before we get onto the rest of the question, let's have a think about this one. We almost have two variables here, x and y, right? Instead of where we just usually have x. The good thing is that we know that x and y also have a relationship. So we can express x in terms of y, or y in terms of x. Alright? So in a lot of optimization questions, you'll get something similar to this to begin with, where you'll have like three variables. You'll have like the thing that you want to maximize or minimize. So here at P, I'm not sure what that is, but we need to find the minimum value of it later on. So you'll have the value that you need to minimize or maximize, and then you'll have two other variables, and usually you want to kind of like get rid of one almost. You want to have a function in terms of only the thing you want to optimize, and one other variable. And the reason for that is because when we get into the actual optimization, what you'll see is that we need to derive, and you can't derive when you have two variables. So let's continue on with the question here. We want to express this in terms of y, in terms of x only. Right. So let's rearrange this equation and do some substitution. If we have x plus y equals 8, we know that y equals 8 minus x. Therefore, subbing that in here, we'll have x squared plus 8 minus x squared. Right. Next, determine dp dx. So we need to find the derivative here. So we're going to have 2x, and then here we have a function to a power, which means we need to use our chain rule. So we're going to take the 2 out the front, take x multiplied by -1. Alright. So now we can probably just simplify. So we're going to have 2x take 2 times 8, which is 16, plus 2x. So we're going to have 4x take 16. Now we need to find the value of x for which p obtains its minimum value. So for that, we need to find when our derivative equals 0. So we're going to go 0 equals 4x minus 16. 16 equals 4x. X equals 4. And now we also just need to check from here that this in fact is a minimum value, so we'll use our second derivative test. So our second derivative will be 4. Right, just the derivative here. Will be 4, and this tells us that the curve is a minimum. Right. So from here we need to calculate the minimum value of p. So all we need to do from here is just substitute this x value in to our p formula. So our p formula was p equals x squared plus 8 minus x squared. Let's substitute 4 in now. We're going to have 4 squared plus 8 minus 4 squared, which will give us 4 squared plus 4 squared, which is 32 units. Alrighty. Let's move on. So this question that we have here is more of a complex one. And even still, a lot of the optimization questions that you'll get in Year 12 will be ones where you're not given a function at all to begin with. So make sure that you are keeping up with these, because in a lot of questions that you'll come across, they might be a little bit harder. So here we have a 400-meter running track, which is made using two sides of a rectangle and two semicircles. So we need to show that x is equal to half multiplied by 400 take pi y. So let's think about this. We know that the perimeter is 400. Right? It's made using two sides of a rectangle and two semicircles. So where x is like the length of the rectangle and y is the width. So let's have a think about this, kind of like intuitively. Alright? What would the perimeter be here? Well, we know that we're going to have two of those x's. So we know that we're going to have 2x being a part of the perimeter. Alright? Now, how are we going to work in those two circles? There's two semicircles on either end. What length do you think those two semicircles will have? If you're a little bit confused, go back to your methods formula sheet, your QCEE one, and have a look at, on the first page, the first box, any formulas in there that might help you. Pause the recording, have a look, see how you go. So these two circles here are actually just the circumference. Alright, so remember the circumference is 2 pi times r. And r here is half y, because remember y is that whole length here. Now we kind of have the circumference of a whole circle because we have two semicircles, if you get what I mean. Those two twos will cancel out, so leaving us with 400 equals 2x plus pi y. Now for part 1, we need to isolate x, so I'm going to take x over to the other side. We're going to be left with 400 take pi y multiplied by a half. Alright. Now what we need to do, because that's what we were asked to prove, is get onto part 2. The area inside the track will be used for other events. Show that its area is equal to that certain value. So now we need to think about the area inside the track. So again, we can kind of break this up into separate parts. We have the area of a rectangle and then the area of the circles. So the area of the track will be the area of the rectangle, will be the area of the rectangle plus the area of the circle. So the area of the rectangle will be x by y. The area of the circle, remember, will be pi r squared. So r, again, is half y. The radius of the circle is half y. So this is what we have so far. Right, now we need to get this in terms of y only. So what we're going to do is we're going to substitute this formula we found from part 1 of the question in for x. So instead of having x right here, we're going to have half 400 minus pi y, because that is what we have in here. Now we're going to pop in what we had before again. So now what we need to do is just simplify, because in the question it was given to us in pretty simplified form, right? So let's try to simplify. Half of 400 is going to be 200. Take half pi y plus pi times y squared over 4. Alrighty. So let's factorize out our quarter. So we're going to have, hold on just a second. Alrighty, so sorry about that, guys. I just realized I forgot to pop the y in here. So I put x, but I forgot to pop that y in. So I just added that down there. And as you can see, now we're going to have 200y take half pi y squared. And now from here, we can actually do a little bit of simplification, right? Because we're going to have 200y, and now we have half pi y squared plus a quarter pi y squared. So they are like terms there. So we kind of have negative a half plus a quarter of something, which will leave us with negative a quarter pi y squared. So just filling out our last steps now, we'll factorize out the quarter, which will leave us with 800. And that's because we have 200y here. So to take the quarter out, the front, you have to put 800 in the brackets, right? 800 divided by 4 is 200, so it's not changing anything. Take away pi y squared. And that gives us our answer. Now we need to find the maximum area that may be enclosed. So from here we need to find the maximum area, which means we need to find the stationary point on that curve. So we're going to find the derivative. We're going to have a quarter outside of 800. Take 2 pi y. Find when this equals 0. So that quarter will already be cancelled out. Take the 2 pi over to the other side, giving us 400 divided by pi. Right? That will be the y value. So now we just need to find the maximum area. Right? So our area formula is, oh my goodness. Our area formula is 1/4 800y minus pi y squared, right, from up here. And then our y value is 400 on pi. So let's go through and find the actual area value this gives us. We're going to have 1/4 times 800 times 400 over pi minus pi times 400 over pi squared. So we're going to be left with 1/4 outside of 800 multiplied by 400. So 8 times 4 is 32, leaving us with 4 zeros there, over pi minus, and as you can see, some of our pi's will cancel out. We'll be left with 400 squared, alright, which is 160,000. We're going to have pi over pi squared, leaving us with just one pi on the bottom. And as you can see, we can actually simplify this quite easily now because we just have pi's on both of the denominators, meaning we can take those two numerators. So we're going to have 320,000 minus 160,000. Right? So what is 320 minus 160? It is 160. And the reason I know that immediately is because 16 is half of 32. Alright? And because they're both in, like the tens of thousands, 32 and 16, because 16 is half of 32, that makes things quite easy. So from here, all we just need to do is a little tiny bit more simplification. Alright? So 160,000 divided by 4. Remember, 16 divided by 4 is 4, so we're going to have 40,000 over pi. And that will be units squared because we have an area. Alright, now let's get into some tips for optimization. My advice is to practice as much as you can. It does get much easier. So I know that especially when you're first starting out with optimization, it seems really tricky and not really that much fun. I know that that's how it feels. But really, don't worry. As you keep practicing more, it will get a lot easier. I promise, especially with all the algebra and coming up with the different equations. I know it is like really overwhelming for some people. So please practice as much as you can. Make sure you work your way up in doing different kinds of questions. So don't just start doing really hard questions. Right, so as you can see, in the question we've done today, we kind of started off with a few easy ones and then worked our way up. So what I'd recommend is get to your textbook. If you're really struggling, try the easy questions. If you still are feeling overwhelmed with those, go back over and do the optimization questions from your Year 11 textbook, because those ones will be easier just to get back into the hang of those ones, or just kind of like learn the content again if you didn't really understand it the first time. Then please, 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 as you get the hang of those easy ones, make sure that you keep progressing and keep doing more and more difficult ones, because they're not going to give you, on your external and potentially on your internal as well, It's very unlikely they'll give you an easy optimization question, and the reason I say that is because we did optimization in year 11, so you've already done it. So getting into year 12, you're not going to get an easy optimization question because that's already been assessed, all right? You're going to get a more difficult one. So please, please, please make sure that you're practicing difficult ones so that when you come across one in an exam, it's not going to be like super difficult for you to do. Then getting on to the optimization, make sure that you draw a diagram. If you're not given a diagram, draw one. If you are given a diagram, especially, I mean, I obviously don't know what your internal exams are going to look like, but in your external exams, they do try to be tricky a little bit. So if they give you a diagram in your external exam or potentially in your internal exam and you really can't figure it out, try drawing the diagram from like a different perspective or just kind of switching it around a little bit, draw the diagram a little bit differently because that can sometimes illuminate an answer. All right? Or sometimes even, I remember in one of my internal exams, I don't believe it was in methods, I think it was in specialist in year 11, our teacher provided us with a diagram in one of our internal exams, and she drew it not to scale. So she told us in the question that, a few lengths were equal, but in her diagram, she drew a one like far longer than the other. So we were all kind of looking at the diagram and being like, oh my goodness, how do we even figure this out? And then the key was to just actually reread the passage of text and realize that those two lengths were equal, but just the diagram she'd given us was tricking us. So my advice there is if you're given a diagram by your teacher or by the textbook, try rereading the passage, try drawing the diagram yourself, because sometimes they try to trick you like that. It's not very nice, but I guess it really picks out the students who pay attention. So draw a diagram if you can. Make sure you include as much information as you can on the diagram, and what I mean by that is not just necessarily the length you've been given or stuff like that. Also point out things like if there's any right angles, if there's any parallel sides, if there's any sides that have the same length, if there's any like angle relationships even. So the angle relationship stuff kind of comes in more with sine and cosine rules and bearings, but any of those angle relationships. So what I'm talking about with angle relationships is like the Z rule, where you have two parallel lines and then you have a line in between them. Those two angles are equal. The co-interior angles rule, if these two lines are parallel, then those two angles will be equal. Actually no, another one of those. Any of these ones, even like the T rule, where these angles will add up to 180 degrees, any of that kind of thing. If you see any of those, make sure you point those out too, because those will always come in handy as well. Make sure you always remember that you're always just looking to find, when the derivative equals 0, to find that stationary point. Make sure you're always checking the nature of that stationary point too. It's really easy to forget, especially after a long optimization question. You finally figured out how to get the equation, you derived it correctly, you got your answer for x, you're like, oh my goodness, I'm done, I'm so excited, and then you forget to just do that first or second derivative test to check the nature of the stationary point. Please, please, please make sure you always do that. Alright, because that is super important and you'll lose marks if you forget to do that. Alright, just a few more ways that you can come up with to form some complex equations if they don't give you an equation to begin with and they just kind of give you some information, maybe a diagram, and you need to come up with the equation yourself. Here are some things that you can, or like formulas that you can remember, alright? So what you probably come across so far in optimization is like going back to that page on your formula sheet, with like area, volume, that kind of thing, where you're optimizing one of those values. But sometimes you can also be required to include other types of equations, ones that aren't necessarily on your formula sheet, some other. Pythagoras sometimes helps. The trig ratios, sine, cos, and tan, sometimes really help with optimization. And then also log equations sometimes also help. And you'll get into those right at the beginning of year 12, so you might have even started those already.